So, what do we see?
What does zinc do by itself, for just in general?
Okay, so we could go through and say, oh, what do each of the reagents do? Okay, that's only relevant if you're going to memorize all the reagents. Are you going to memorize all the reagents?
We'll understand them.
Okay, so to understand them, you don't need to know what zinc does. You need to go through and look at the change within the chemical reaction and start to predict. Okay, so if you're in a system where you are not given products, now you need to know more about what it does. You're not being asked that. You're being asked to look for the patterns and try and predict what things changed and how they potentially changed. Once you know what things have changed, you might be able to go back and say, that's what zinc is doing. There are clues given around that give you some context about what that zinc is doing, but I would argue that's a secondary question.
Well, the BR left.
Okay? The BR left. Okay, I can accept that. We broke that bond. Okay? Where did that carbon end up?
Probably attached to the other group, the RCN.
So it's attached over here. Where is that blue dot in the product?
The center carbon.
It's that center carbon. Okay, cool. What else?
There's ketone groups.
So you're stating what is present. What we're trying to do is find where those pieces are. So it isn't just, I see a ketone, okay? Because we're beyond that. Right now, what we're trying to do is find the patterns of where those things ended up. We want to be able to predict where these things ended, where they reacted, where they moved, so that we can predict how this reaction potentially functioned. Okay? Particularly back to the question, you're trying to identify the nucleophile and electrophile. So one thing we could potentially do with color coding, that goes to R prime, right? Oh, look, there's R prime. It also goes out to a CO2R double prime. What is CO2R double prime? Well, there's a C connected to an O, connected to an O, which sounds an awful lot like CO2, which is then connected to our double prime. So if we're looking at this reaction in blue, we've now covered all of those pieces. If we look at the product, we're still missing stuff. Where is that stuff in the starting material? Let's try it this way. Do you see an O? There's an O in the starting material?
No.
There's an O in the product. So is looking at the O useful? No. What did you see?
The R group?
Yeah, hallelujah, we got an R group. That R group has shown up the same in both cases. That R group is connected to something, right? What's it connected to? Right, we can go with nitrile. What is a nitrile?
It's a carbon triple bonded to nitrogen.
Lovely. It's a carbon triple bonded to a nitrogen. What can you tell me about the nitrile group? What kind of bond is that?
Polar.
Do better.
Protic.
What?
Is protic a polar?
So we could try and throw protic at it. That would be talking about solvents. Since it's not a solvent, that's a questionable assignment. Okay? Push to it, is it protic?
Well, it's
Does it have a hydrogen bonded to oxygen, nitrogen, or fluorine? No. So is it protic?
no.
No. So protic as a statement was questionable because it's a reagent, not a solvent, and straight up wrong. What is polar?
The bond,
What kind of bond is that?
triple bond.
Ah, so there's a fun statement, a triple bond. And if we remember back in OChem 1, I told you explicitly there's some bond names we should never, ever, ever use. What were those bonds names? It's a hint, there's 3 of them. Some bond classifications that are horrendous and should never get used in this class.
Like
Single, double, and triple. So calling that a triple bond is immediately going to make me go, ugh. Yeah, that's a reasonable response, though I have a feeling that was in reference to your coffee. Okay. So what kind of bond is it? It's a polar pi bond. What was this chapter about? Oh, cool. How did polar pi bonds react? Okay. That carbon is particularly electrophilic. Okay. Why?
All the electrons are going to nitrogen.
Why would the electrons move to the nitrogen? Nitrogen is more electronegative than it. Okay? So that would generate a negative or a partial negative. I'm going to go with partial negative formally here. And we could say, oh, that means it could act as a nucleophile. How many times did our oxygen or our nitrogen act as nucleophiles in our reactions?
Like this one.
We just spent 6 weeks, 5 weeks talking about this. How many times did you see the polar pi bond, the polar element, act as a nucleophile?
Not at all.
Yeah, not at all. Okay? And we talked about why. Why would it be less likely to act as a nucleophile?
Makes it hydrogen.
Hydrates are talking about reacting water with the electrophilic site, not with the nitrogen or our electronegative atom. Why did we talk about the nucleophile being unlikely?
Is it steric hindrance?
Nope. Though I'm sure Anthony would love that you suggested steric hindrance, but no steric hindrance. What atom is picking up those electrons? What atom is picking up the electrons to make this site partially negative? Nitrogen. What can you, or, because we didn't talk about nitrogens all that often. Oxygen. What can you tell me about nitrogens and oxygens? Oddly enough, it goes back to your product statement.
The active bases.
They're very electronegative. Because they're very electronegative, are they willing to share their electrons very much? No. Okay? Which means they don't fall towards that nucleophilic characteristic very much. If we push to the carbon, why would it be more electrophilic? Well, if we draw that resonance, what happens? The nitrogen has its octet. Does the carbon? No. Which one's more reactive? Missing octet or having an octet? Missing octet. So that's the driver of all of this chemistry. Does that mean the electronegative element in our polar pi bond can't act as a nucleophile? No, it absolutely can, but you're looking at very special circumstances to force it to happen. Okay? Those circumstances are relatively minor in the grand scheme of things, so we didn't talk about those. Okay? So while it is nucleophilic, it is unlikely. Okay? So this now pushes us further back. We now have that electrophilic carbon. Okay? Where is that electrophilic carbon in our product? What's that? Huh? Which central carbon? Because I would argue the central carbon would be that blue dot, and you're telling me the red dot and the blue dot are the same atom?
On the left carbon.
That probably makes sense. Okay? Does that set up and become potentially problematic for us? Well, do I have the nitrogen anymore? No, I have the oxygen. Could I convert the nitrogen to the oxygen?
Apparently, yes.
How?
That's a good question, but product says it's possible.
Does that have to do with zinc?
Don't even have to worry about zinc yet.
Is the CO3?
This is effectively going through your imine chemistry. Nitrogen versus oxygen. Those are reversible reactions. You can shuttle oxygen and nitrogen on and off of a structure almost irreplaceable in identical conditions. So this is for sure imine-based chemistry. Okay? That imine chemistry typically needs just a single polar pi bond and not three. The three bonds there does make it a little bit more challenging, and it needs a little bit more oomph to actually get that thing to go. Okay? Do we need to worry about that yet? Because if we go through and look at our product, what things changed? You just addressed one of them.
There's no nitrogen?
The nitrogen versus the oxygen. So that pi bond changed. What else?
Well,
Said another way, what bond is not highlighted?
they're not connecting the two?
Yeah. So if we're looking at the overall changes in this reaction, we're doing the purple reaction and the green reaction. That's it. Okay? The question becomes is how do we get that to happen? Well, which one do you think is more challenging to do?
Purple?
Why is the purple one more challenging?
Because you have to switch out the oxygen, the nitrogen, the oxygen.
And why is that more challenging?
Because I don't know how to do that. Or I don't recall how to do it.
Okay, that's better. But you recall how to make a carbon-carbon bond?
With the negative carbon. The
Okay.
negative and positive carbon.
How easy is it to get a negative carbon?
Not easy.
Okay. How easy is it to get a negative oxygen?
Pretty easy.
Hmm.
So maybe the green one's the easier one. The harder one.
Okay. If we look at that carbon-oxygen bond, we're looking at a polar bond. We need negatives and positives. The carbon's going to be positive all the way through that because it's connected to an electronegative element. Okay? I don't want the nitrogen in my product, so I have to somehow put oxygen in and somehow cycle through to get the oxygen to boot the nitrogen. Okay? And you may not know how to do that. That's a different question. Should. Okay? That's a different question. Okay? If we look at the other one, the green bond, that's a positive and a negative. Again, same system, positive and negative, but now I'm bringing in a negative carbon. With the purple one, I'm bringing in a negative oxygen. Yeah, that happens. Yeah, sure, why not? Okay, how is a different matter? Negative carbon, is that particularly likely? No. Did we learn about negative carbons? Cool. Okay, so maybe what's happened is you're falling back on the content you remember that negative carbons are easier to make. Cool, I accept. Look at our starting material. Do we have a negative carbon? Interesting. The plot thickens. Okay? We're looking at our red dot, I'll make that a dot now, versus our blue dot. Both of those carbons as drawn are what charge? Positive. I somehow need to make them talk to each other, which means one of them needs to be negative.
One on the right, you can form an enolate.
The one on the right, we could try to form an enolate. Okay, that's possible. What would happen to the carbon-bromine bond? Good answer, nothing. Okay, by forming that enolate and removing that hydrogen, that's absolutely fair game, that's awesome. I like that logic. But then you're making your negative carbon and you haven't affected the bromine. Okay, and we know the bromine's gone. So is there something else we could do that could potentially tackle the bromine and get me a negative carbon? How else have I formed negative carbons? By removing hydrogens, that's exactly what she suggested. Grignard. And what did we do in the Grignard? What's that? Oh, we added magnesium metal to an alkyl bromide. The magnesium inserts itself into the bromine carbon bond, making the carbon negative. Are we adding magnesium? No. We're adding zinc. Are we adding zinc metal or zinc ion? How do you know the difference? You're laughing now because are you laughing because you think that was stupid? You heard it from her, not from me. Okay. For it to be zinc ion, what charge must it be? Positive. Do you see a positive charge written next to it? No. So is it an ion? No, it's a metal. Okay. Let's push on that even further. In Gen Chem, you learned about zinc. You actually had to do nomenclature with zinc. Oh, yeah. You're like, I didn't learn anything in Gen Chem. I get it. Okay. And if we made the compound zinc chloride, what was our formula? So I'll give you zinc, Zn. What's chloride? Cl. Proper nomenclature, we have to ensure that that formula is balanced. Do we know the charge on chloride? Subtle, dagger stab through the heart. That's okay. I mean, I could turn around, but I don't think that makes it feel any better. It's a -1. What's the charge on zinc? Okay, we can get a couple things here. I got kind of a shoulder shrug, like, I don't know. Okay. Okay. It's a metal, I don't care. Mike, this is OChem, shut the hell up. I get it. Okay? But we're now in systems that we start to move to things that aren't just organic compounds, and you need to be able to extrapolate to those possible scenarios. That's what we've been talking about. It's what I've been telling you. Do not memorize, but think about the chemistry associated with those things. And if we've built that chemistry up, we have the potential to make that application. If we are not working on building that chemistry and instead just memorizing to get through, we're in a problem. Okay? Which is a bit problematic for me after having said all that, because guess what you should have done with the charge on zinc? Do I need to record it too? I should probably record it after yelling about memorization. You were supposed to memorize the charge on zinc. You're supposed to memorize the charge on zinc is a +2. So that when we look at the compound zinc chloride, it's ZnCl2. Why does this become important to us? Magnesium, when magnesium reacted in the Grignard reaction, what did it do? It's a harder question. The set mechanism. Set mechanism was single electron transfer. How many electrons did magnesium single electron transfer? It rhymes with shoe. 2. It does a single electron transfer to the bromine, then it does a single electron transfer to the carbene. 2 electrons. And if I have zinc metal, and I know zinc metal wants to become zinc ion of a +2, what does the zinc metal have? 2 electrons. Then what could it do? The exact same thing, and insert itself in between the bromine and the carbene, effectively creating a carbon nucleophile. That carbon nucleophile could do what? Attack, breaking one of my pi bonds. Did I want all those pi bonds to my nitrogen? No. Here's the perfect scenario to set up breaking some of those processes. By finding the positives and negatives, I can start to think through where those pieces moved and start to address where those chemistries lie. Okay? That's what you should be trying to get to. Okay. For the record, is this easy? Okay, you should move on to a more advanced organic chemistry class if you find this easy. Okay, this is not an easy process. You're trying to use your reasoning based off the stuff that you've partially learned. Because let's be honest, you haven't formally learned it yet. Even after the test, you probably won't have formally learned it. You're processing this content. So what you're trying to see is how to apply that to new scenarios. That is insanely challenging. Okay? But what we will have created after that first step is now the green bond between those with a polar pi bond to a nitrogen, not to an oxygen. Well, what would I need to add to get rid of the nitrogen? Oxygen. Yeah. We'll pick up a hydrogen from our solution. Officially, there's our green. What kind of oxygen do I want? Was that double prime? What do I want that new oxygen to come in and do? Act as a nucleophile. Donate electrons in, which would break the pi bond. Then what do I want it to do? Do it again. I've only broken the pi bond. What do I need to break? The sigma bond. So I would need that oxygen to attack twice. But oxygen has to show up as neutral. So what are these bonds connected to? If they were connected to carbons, would that oxygen do this reaction? No, why not? We would have to lose the carbons. That's not particularly likely. So what could I attach to that oxygen that I could lose through the course of this reaction relatively easily? Hydrogens, which would mean in the course of this reaction, those hydrogens or that oxygen molecule is now acting as what? LSD. Really? Come on. That was a pretty good clue. What must those hydrogens act as? We want those to come off. We want them to come off as what chart? At least you got it. Apparently it's an age thing. Everyone's like, what the hell is that? Okay. Those have to act as acids. Right? So what might we add to the solution to help them act as acids? Bases. What does potassium carbonate act as? A base. Where the hell did this H2O come from?
It's aqueous.
There's a reason it's aqueous. Okay? They didn't specify the water as the reagent doing the chemistry because it was there as the solvent to force the reaction to occur. The base is used to help force that reaction to happen. So what we end up doing is a Grignard type reaction followed by some imine carbonyl conversions. It's almost like if we look at the clues behind the name, Grignard-esque and imine carbonyl convert, because that's exactly what's happening. But this is using reagents that are outside the realm of our visibility, but if we start to look for those patterns, we can start to make those assumptions and those logical flows based off of what you've already seen. That's pretty neat, right? Why is it extra neat? Well, depends on who you talk to, and admittedly, I'm not the best person to talk to. This reaction was known as the Blaze reaction. Why? Some dude named Blaze ran the reaction and was like, woohoo, wicked, look at this name. And does it do the same thing as chemistry that's already discovered? Yes. Why do you get to attach your name to it? Because your name is Blaze and it's cool. I mean, everybody wants to be called Blaze, right? What's that?
I said even though the spelling's
I think I'm pronouncing that right? Is that, maybe it's not pronounced Blaze.
or is it like
It could be. I would hope it's Blaze. If it was mine, I'd be like, no, bro, it's Blaze. Don't be calling me Dr. Blase. For the record, I'm not a doctor, but I almost guarantee that Blaze, and probably Mr. Blaze, was a doctor. And not to take away from them, because I'm sure they did a great, phenomenal job behind all this chemistry. Right? We love people with named reactions.
What would you name a reaction if you could name one?
I wouldn't.
So you wouldn't name it anything?
I wouldn't.
So you wouldn't name it like cock or giggles?
Nope. Nope. But I do appreciate that there's some people that have a good sense of humor. This is a fun compound. It's got arsenic in it. Okay. If you put a nitrogen and or oxygen in it, I think it's called pyrrole. I don't remember what nitrogen is. That might be pyrrole. I don't know. But in any case, they went through and they kind of put it all together. It's arsenic, so we'll call it arse, but it has the same aspect as you have with the pyrrole, so we'll call it arsole. Say that one 10 times fast. I think that's hilarious. You all have no sense of humor. Okay, in any case, what's happening here? Oh my God, there's way too much going on. I don't want to worry about it. Just break it down, step by step, navigate where you want to look. So where do you want to start your conversation?
Well, if I bond from the triple bond gets removed, that's what's
Okay.
happening.
So what you're saying in your conversation is you don't care about the final product, and you're only looking at what's changing in that first step. Awesome, I love it. Okay. And what changed? So now you can come back to me.
Well, they combine them and that triple bond got removed.
Okay. This triple bond somehow got removed. Okay, we lost that. Okay. But how? Where? Ooh, I like the hand gestures. It's a little like magic, but you know. What are you seeing?
That triple bond connected to the double bond. Sorry, I'm using the words you don't like.
Oh, shit, I missed that too. So the one that has lots of polar pi bonds.
I just seen that it's rotated and that pi bond became a different type of pi bond, whatever, and it's connected to the EWG carbon.
Because this is what I believe your hand drive was doing.
Yes.
Lovely. Okay. That's what you're seeing happen. So now the question becomes, how?
So somehow we lost the hydrogen on the left and we gained another one.
So you looked at this even closer and noticed that you also lost that hydrogen. Interesting. Okay. And then had to somehow gain it out there. Cool. What? Okay, how does it work? So what's going on with the chemistry? So what does it mean to be a Michael donor? What's happening?
Well, hydrogen leaves and carbon nucleotides with that one.
Okay. So what you're suggesting is that we're going to axe this guy, which would make that carbon what charge?
Negative.
Cool, so we're going to color that. We're saying that carbon there. So that carbon would become negatively charged. Is that an easy bond to break?
No.
Why not?
It's the carbon doesn't want to be negative.
Okay. Well, if that's not an easy bond to break, should it break? No, so you need to explain why we can make that carbon negative. Okay. Full disclosure, this one confused the living bejesus out of me, and I would argue already you have moved beyond where I saw first. Because where I saw first when I saw this reaction was I saw that triple bond. Okay? And I said, those electrons must have come across and attacked. Would I expect this carbon to be negative? That red carbon to be negative?
Yes.
Okay, we heard yeses and nos. For yes, explain to me how it becomes negative. And if you want to pass, that's okay.
Trying to think through it. I mean, yeah, pass.
Okay.
I
You said it was positive.
Yeah, the electrons are being pulled down to oxygen, so that would be positive.
If we go through and look at that structure, the reactivity is our polar pi bond, which is pulling the electrons in that pi bond out, which means these electrons swing down, which means that top carbon carries a partial positive charge. So the initial assessment of that pi bond being our nucleophile was actually wrong. Okay? So that means we have to make the green carbon negative. Well, how can we make that green carbon negative? This is where having observed that there was a hydrogen that is no longer there in our product comes in play, because if we're going to remove that hydrogen is likely going to get removed as what charge? Positive. Shouldn't be an H negative because
H negative sucks.
H negative sucks. Okay? That cannot stabilize the charge well. The positive is somewhat reasonable. Okay? So we now have to explain why that hydrogen could get removed. Okay? Well, the explanation behind that would have to do, and I can't believe I did that. Oof. Can't even draw. We would need that to be a negative carbon, right? Okay. Well, how could I possibly get that to be negative? And then I'd have my H plus chilling out. We could say strong base. What's written over the arrow? Nothing. Okay. Officially, I think it was a bit misleading. It does say pyridine. Actually, I gotta lie, I gotta check something. Never mind. Pyridine means something else. Does it say there's a strong base? Okay. If I know that hydrogen must be removed, what does that mean about my green negative carbon?
Acid.
This structure has to happen. What does that mean about this? Does it exist? If it does not exist, do we get our negative carbon? So, does it exist?
Yeah.
Yes. For it to exist, what must be true? True. But if I drew this out, would you tell me I was full of something unpleasant?
Probably.
Yeah, that probably goes without saying, but... Well, why not? Why is that bad?
There's nothing to promote that chemistry.
What do you mean there's nothing to promote that chemistry? Getting at the right idea, yeah.
You don't have to happen on its own.
Why does it not happen on its own?
Those are non-polar bonds.
Carbon to hydrogen that we're talking about breaking are also nonpolar. Why is the black circle not good? It's inadvertently turning into a good review. Why is this one okay? Oxygen is more electronegative than the carbon, which means the oxygen can stabilize that negative charge. So if we're talking about our original reaction all the way to the far left, if we know that hydrogen has to come off, what does that mean about that negative carbon? It must somehow stabilize the charge.
Resonance.
Where's the resonance? This one gets a little shaky.
The nitrogen has a lone pair.
Okay, and this was the one that bit me. If the nitrogen has the lone pair, what happens?
It can form. It would go down and it would kick the pi, so there'd be the negative.
So what you might try and run as the argument is that this comes down and that these electrons are what swing out.
Yeah.
Okay, that's a possibility. And then we could talk about the possible products that could come out of that. Is there another way you could remove that hydrogen? And this is now asking mechanistically, because what you suggested is one mechanism, which is different than the formation of this H+. What does EWG stand for? Ah, there we go. If you don't know, what should you do? Ask.
What does it stand for?
Okay, what does EWG stand for?
It's electron withdrawing.
Electron withdrawing groups. And what would electron withdrawing groups do? Withdraw the electrons, doing what to that negative charge?
Stabilizing.
Ta-da!
That's so stupid.
Okay. So now which mechanism is more valid? Where we go through and remove that hydrogen, or we run, as you suggest, with the nitrogen donating electrons up and in? How would we decide?
Run it.
We would have to run it. Not just run it, we would draw out our mechanisms and be like, okay, here are the intermediates that I think come into existence based off of this mechanism. Do I have evidence to suggest that that intermediate is actually in solution? Okay. That is a much harder question. That goes beyond what we actually go through and need to know. At this point, all we're trying to do is think through the possible ways that this could occur. Okay. To the name behind it, you're like, oh, it was obvious, it was Michael. Yeah, what about that screamed Michael to you?
Absolutely none of it.
Okay, so just because we have a name doesn't mean it stands out. Where's the Michael to do with this? This is the Michael acceptor. I can't spell Michael. You'd wonder why I can't spell Michael. Okay, and the other one becomes the Michael donor. Why? It was the one supplying the electrons. The Michael donor is your nucleophile, and the Michael acceptor is the electrophile. Depending on what mechanism you go through, you may end up with a couple different steps, but you're going to end at the structure that's shown. That's this big, ugly structure that we may be like, oh, God, I hope we're done. Except, we wouldn't call it Boltzmann-Rotz. We even had to name after two people. For heaven's sake, if we're going to name after two people, I better do something cooler than one step. What can it now do? How can it form a ring? The nitrogen, as a source of electrons, could react with the polar pi bond of our carbonyl. And if that somehow looped around, we would have a 1, 2, 3, 4, 5, 6-membered ring. Are 6-membered rings stable? Yeah. So someone may have just done the Michael reaction, or like, oh, this is all I wanted. And then what happened? Not that. And they're like, what the hell happened? Okay? And they continued to run the reaction, and they kept getting not what they wanted. And eventually what happened is they isolated, looked at the product, and they go, oh, we had pyridine. What? How the hell did that happen? Oh. 6-membered rings are stable. That could do that imine formation. And there we go. the carbonyl is replaced by that nitrogen. That's some pretty neat chemistry. That's doing a whole lot of stuff. Hats off to Bowman. Sorry, Bowman. Sorry, giving credit to somebody else. Is it Boltzmann? Different. That's a physicist. Kind of get it? What you're trying to look for is those patterns of chemistry that you've seen in other scenarios and scaffold and build upon it. That's the goal. Okay? This next one should scream all sorts of problems. Why does this next one scream problems? Oof isn't appropriate. That was my response too. The name might give it away too. You can look at the structures or the name.
It does something weird.
Rearrangement? Yeah. It's a rearrangement. You've shuffled the atoms around into a different configuration. Okay? And anytime we got rearrangements, I can almost guarantee those things are going to be freaking named. Okay? They're just doing really interesting chemistry, and that chemistry is why we would go through and do this. So if we're looking at the overall reaction, trying to predict how this reaction happens, what majority type reaction does this appear to be? What do you think?
So like acid base.
Okay, acid base means all we've really changed is hydrogens. Is that all we've done? Okay, I would argue it doesn't fit the acid base system. Yes, there's acid base stuff there. What other stuff do you see happening?
Substitution.
I would probably lean more towards a substitution. Okay. That oxygen is somehow coming back and attacking the carbonyl, which forms a goofy three-membered ring. That three-membered ring is highly stressed. It's going to pop, and as it pops, it does a rearrangement to shuffle and stabilize the intermediate species. Okay. Do you need to know that mechanism? No. Do you need to know this reaction?
Yeah.
It's shown up on ACS tests. It has. Okay? And if you're like, oh God, I don't want to have to memorize it, then don't. Okay? What you would hope for is looking at the answer choices and being like, what the hell is going on with those answer choices? Where the hell did that come from? And if you encounter something that's like that, where the hell did that come from? That might mean that you're looking at a rearrangement. Okay? Which to me would also suggest that what should you do? Move on. That's hard. Don't worry about it. Come back to it later if you get a chance, and then try and reason your way through. Kind of, sort of?
They're able to like take questions from an exam too and like change them so.
From the practice exam? Yeah, we could try and do that too.
I mean, for like the exam we've got to take on Thursday.
No.
Well,
Because I don't want you to memorize answers. I want you to understand the chemistry that's going on behind it. That's why. Kind of like the entire philosophy for the last 20 weeks that you've had chemistry with me. You want to look at another one? Big and Ellie? That one's fun. What do you guys think? One molecule acts as both a nucleophile and an electrophile. I haven't looked at this in a long time for the record, so I'm looking at it effectively with fresh eyes.
is it the third one?
I don't know what third means.
Bottom right?
Yeah.
Bottom right. Let's go through, take a look. If that nitrogen went here, that could shuttle all this out. And then you just get the imine how do you get that pi bond? That. Okay, so I could see that on that end. So there, what is it acting as? Nucleophile. Where's the other chemistry? So that would be forming this bond, right? Would we predict the other nitrogen to act as an electrophile? Why not? What do electrophiles act as? Cool. Why would nitrogen not act as an electron acceptor typically? Because it has lone pairs, so it would likely act as a nucleophile. It would likely donate electrons up to this guy, kicking out that thing. I could be wrong, for the record. Okay, so there are those connections. What's the last new connection that we need to make? Is that another way? There's that structure. There's that structure. What's the last bond that needs to be made? Well, except Charlotte's hand waving there. That bond. So I need to connect the blue to the green structure. And I would need to connect this green dot to this blue dot. How could I possibly do that? What's the chemistry available to the green dot? Electrophile, nucleophile, or none of the above? For the record, I would accept 2 of those 3 answers. You got a 66% chance of being right. Okay, acting as an electrophile. Okay, how does it act as an electrophile? What would it need to do? Okay, which means the blue one is acting as. Does that carbon have any electrons? No. Okay. What does that suggest? So the green one's not acting as an electrophile, which means it must be acting as nucleophile. Okay, do you see any electrons? There, it has 2 hydrogens, in fact. Okay. So that's an alkane functional group. Are alkane functional groups particularly reactive? No. Which means none of the above. It doesn't react. Yet it does. How does it react? What had to happen before it can run the chemical reaction? It would have to lose a hydrogen so that it could become negatively charged and act as a nucleophile. So in our 3 answer choices for that green carbon, definitely cannot act as an electrophile because the blue one can only act as an electrophile. They only have that choice. None of the above, it's all friggin' alkanes. There's no reason alkanes should react. For the reaction to occur, it must become a nucleophile to complete this, which means that lower left-hand corner is acting as both an electrophile and as a nucleophile. Okay? Why is one of those hydrogens acidic?
Because you have the 2 oxygens, which would probably, one of those has to be ketone.
If we expand the structure out a little bit, why is that hydrogen particularly acidic?
It's between 2 carbonyls.
It is resonance stabilized between 2 carbonyls. The pH or the pKa of that hydrogen is in the 8 to 9 range. That's very acidic as far as carbon structures go. That's going to activate very, very quickly, be deprotonated by anything remotely basic in solution. Ethanol might even be able to pull that off. Okay, weakly, but it would probably be able to pull that off. You now have the nucleophile, which can go through and react with that blue structure. Should all of this chemistry happen at once? Probably not. Why not?
It's a lot of arrows.
Do better.
I want the charge has to form first.
We do need to form charges, yeah?
A lot of reactive sites.
A lot of reactive sites. Why else? For those people in lecture or the tutoring center, I've already been off color today, so we're going to go ahead and add to it. How often do you see threesomes, successful threesomes?
Not frequently.
Yeah, not frequently. Yeah, that's pretty rare. That didn't happen very often. If we were going to say this all happened at once, what had to happen? 3 molecules all had to come into perfect alignment to allow all of this electron transfer to happen in one single step. Is that likely?
No.
No, which means
Not simultaneous.
not simultaneous. I go out on a limb, polygamy doesn't work. At least as far as chemistry goes. Okay. Maybe people can pull it off, I don't know. Quite frankly, I don't want to discover. Okay. Chemistry, we don't do that. You got to break that down into individual steps. Okay. Once 2 of those 3 linkages have happened, the third one's going to happen really, really, really fast because you've already brought the structures, all the pieces together effectively into that perfect alignment. That last linkage will go really, really, really fast. Okay. But I would bet the first one's probably okay. The second one is going to be challenging, and the third one is probably going to be pretty lightning fast. Why would the second one be challenging?
What's the second one?
So there's an interesting point. Did we specify which one happened first, second, or third? Nope. So why would I just blanket statement say the second one is going to be the hardest to form?
It's the hardest to figure out which is nice.
Think about what's happening as far as chemists or organic chemists go. We take a bunch of reactants, we put them into a pot, and we shake it, and we hope stuff happens. That's how chemistry works, okay? Or organic chemistry works. It's very inelegant, okay? Very crude, very brute force. And if I shake those systems, how likely is it that I'm going to be able to get 2 molecules to collide? Not likely, okay? But getting those 2 molecules to collide will happen eventually. Okay? If I look at the next reaction to happen, it's not just the next random molecules colliding. It's the next reaction where it's already reacted and I have another reaction. So now I'm effectively stacking 2 reactions back to back within that system. The odds that I'm going to be able to pull that off go down. That's harder to go through and pull. Why is the third one the easiest? It's intramolecular. All the pieces are already connected. They just have to spin around on top of each other to make that final linkage. Okay? That's shaking my own hands. I can do that. Kind of makes sense? For the record, that also does not mean I'm right. Just looking at kind of the odds behind how those reactions can cycle. How are we feeling? You regretting letting me choose? You have a migraine? Say that sounds like a regret. Do you want me to keep choosing?
I mean, this is good practice no matter what.
Oh yeah, we it looks like maybe do an IR.
Holy mother. I mean, come on. Doesn't that just look sexy? Wow, what the hell is going on with that? Dude, hats off. They need a name on that one.
That one deserves the name for whatever's going on over there.
Das. I think I see it.
It's cold.
Yeah. One of the things you'll find if you actually start looking at reaction conditions is that we will start getting really cold with a lot of our reactions. Why would we get cold?
Because they produce a lot of heat.
These reactions can be a bit explosive, so you want to limit their reactivity, and you can limit their reactivity by slowing them way the hell down. So what do you guys see? Took me a little bit. I think I've got an idea.
There's positive and negative nitrogens.
Okay, so positive and negative nitrogens. But are those positive and negative nitrogens necessarily relevant to me?
No,
Why not?
they don't show up in the product.
They don't show up in the product. Okay, so what I'm looking for is what's in my reactant, what's in my product, and trying to figure out how those things could connect. So what do I see that would allow me to make some connections? Cool. Do you see a carbonyl in the product? No. Okay.
There's 2 R's.
There we go. Okay. Less focus on the carbonyl and more focus on the things that we know are still present. We have the R and the R prime. Okay. And if we look at that, the R and the R prime are connected to a carbon, and I would need another carbon. And if we go back and look at that starting structure where the carbonyl was indeed, I only have 1 carbon. Okay. And if I was going to color code, well, actually, it's not going to matter as far as color coding goes. Okay. So I could then go say, well, I have the carbonyl, and what is that? How it happens to the carbonyl? Right. It disappears. Right. It's gone. Okay. So what does that mean as far as the red carbon? How do we think it acted in this reaction? Why do you think it acted as an electrophile? Oxygen takes the electrons. Cool. So that carbon is likely acting as an electrophile. So now let's go through and look at the ugly, disgusting structure. And this is where we might lean on those nitrogens.
They're positive and negative, so they could potentially resonate.
Oh, okay. And we could decide to focus on wherever we wanted with that positive and negative, but where I would lean is more on the negative than on the positive. Okay? The negative to me is my source of electrons, particularly if I'm talking about resonance. I want to push on those and see what they could do. So what could those electrons do? Where could they resonate?
It could resonate down to the positive nitrogen, but that would exceed octets, so you'd have to kick some electrons out of the double bond underneath it.
Onto what?
The carbon.
Onto the carbon, which means the carbon becomes.
Negative,
Why is that really powerful for us?
because it could do the chemistry we want it to. Without the headache.
If I go through and look at my final product, I've got a connection between the red and the green. Okay? I've got a red that's electrophilic, and I just, by identifying resonance, identified that my green is negative. It's nucleophilic. Okay? Why would I put this in a section that is similar to, say, the Wittig reagent? When we consider the Wittig, what was our Wittig reagent? Right? A negative carbon next to a phosphorus. What did we just show with our resonance? It's the exact same chemistry. How wicked. And what did the Wittig react with? Carbonyls. What is this weird, wicked nitrogen structure going to need to react with? A carbonyl. How do it do it? I don't know if, cross that bridge when we get to it. But, pieces are coming into alignment. Kind of, sort of? Okay. Some other things to potentially consider as we look at this. A lot of stuff also still has to happen out of this. I want to draw out this resonance structure real quickly. I don't know why I just try to draw that part, because I don't care about that part. Right? Do we see anything that stands out in that structure that might make us go, that looks vaguely familiar? That sounds kind of similar to the Wolff-Kitchener reagent releases nitrogen gas. Diazomethane, when talking about carbines, releases nitrogen gas. So this is taking advantage or leveraging some of that same chemistry. Okay? Are we still going to do some wicked crazy stuff? Yeah. Okay? And enough that I don't know that I actually even want to attempt to show arrows within that, because I don't think it's worth the trouble. Okay? But what I want you to start to do is draw connections and parallels back to other reactions you've seen to look for those pieces. And when we start to draw out those resonance structures, hopefully we start to recognize those patterns and can recognize how these things work. Yeah?
Yeah.
Cool. Don't be so depressed. That was kind of neat. Yeah? The best stuff in life is complicated. Get married. I'm married too. You're saying my marriage isn't complicated? Yeah, that's what I thought. It's also one of the best things in life too. Try whatever you do.
How's it complicated?
Cross that bridge when you get to it. Kind of makes sense?
Yeah.
Okay. I believe the rest of this was going through and looking at all these other things. Oh, in fact, N2 looks an awful lot like that carbene chemistry. Okay, and what's the and? You guys called it out. The Wolff-Kitchener, I think, is what this question was trying to get at. Okay, and so we get lots of different crazy, goofy things going on. You can see actually there's that nucleophilic attack. Okay, it's coming straight out of that system. We're forming effectively the Wittig intermediate. Okay, that Wittig structure, yes, needs to fall apart, and it is a mess. How it falls apart. Right. Yeah, that four-membered ring, which looks really familiar. That's the Wittig. Right? So what might happen? Then we could add some curved arrows to figure that out. I genuinely don't know how to answer that question, for the record, so don't sue me. Huh. I don't think I like the N2 being drawn that way.
Are the lines around the oxygen supposed to represent lone pairs?
Yeah, old people. I mean, old people are great. Old people are great. So, any ideas on what could happen with those arrows? I mean, it says add curved arrows to the last structure shown to the left and draw the resulting products. Apparently I don't know my rights and lefts. That's got to mean the last structure shown to the right, because the one on the left doesn't work. So how could we go through and do this? Any ideas? You guys want to give that a swing, or should we let it go?
Let's say I heard an article rearranges to give time to help the nitrogen gas to come up.
So you want to rearrange.
And then
Okay, let's make sure I got it right. And then that could eject.
then all the other chemistry reunited.
And then we could shuttle that over. And that over. But we got a couple problems. Sorry for that long bond. We have that hydrogen there. We don't have the triple bond. I'm not seeing it. That doesn't mean I know what's going on. I haven't looked at it in a long time. We can try and advance the slide, or not advance the slide, but scroll down and see if I provided an answer. Yeah, I didn't, because I was a jerk. But yeah, we've got to be doing, oh no, it has the double bond, so we don't have that. I drew that structure wrong. I might have to look at it later. Oh, because we're also done with time. Okay. But I'm going to poke at that in just a second. So what we're trying to do is consider what's going on within these systems and kind of look for those patterns, those positives and negatives, and navigate what things could change as we move through it. That's the goal of organic chemistry, is to play with this. And I use that word very not carefully, like insistently. This should be playing. You're playing with the structures to see how they work. Okay? You're trying to solve those puzzles. Okay? The more you can turn it into a fun game, the better off you'll be in the overall course, because you're starting to recognize patterns and follow those arrows. Okay? Follow the electronegativities and the resonance. It will help. Okay? Fully understand not everybody can see it as a game. In which case, study. Memorize those things. Okay? Theoretically, at this point, I won't ask you to show me, but everybody should have a sheet of paper with the, oh crap, I need to memorize this. And if you don't have that sheet of paper, I don't know what to tell you, man. I've now told you a whole bunch of times. You should have that sheet of paper of this is the stuff I need to have memorized, and that is what you should be looking at right about now. Okay? Because when it comes to the exam in 2 days, you don't have enough time to learn any of the content. What you're trying to do is cram and memorize as much as possible moving forwards. Okay? Small bright spot. When I first moved to this textbook, the Cardi textbook, the students that took exam 2 did exceptionally well. So well that I actually gave them exam 3 content in the very next class period, and they also aced it. Okay? So if you're recognizing these patterns, what you will start to find is that I'm not giving you anything new. It's the exact same chemistry again and again and again. And it's just a slight variation that makes everybody go, oh my God, it's new. It's not new. It's the same stuff. Okay? Unit 3 is a pretty huge copy of Unit 2. You've already had some experience with it because the Grignard that we did was officially Unit 3 content, believe it or not. Right? And then Unit 4 is our last unit, which you can take or leave however you want to deal with. Personally, I would leave it alone because I don't think it's worth that much in the grand scheme of things. Much better than, say, first semester, where the last unit actually had some sizable points. Okay? You all have this. You can do it.